In this session, we're going to look at the masonry notes, details, and prototypes. My name is Sam Rubenzer. I am the founder of Force Consulting and the managing director. I'm a licensed structural engineer in the state of Illinois and a professional engineer in many Midwestern states. I have an engineering degree from the University of Minnesota and a MBA from Marquette University. We at Force have worked with the masonry industry for many years and been a consultant to Structural Masonry Coalition since 2010. So in this session, we're going to review some definitions of masonry items. We're going to discuss some notes for structural drawings. We're going to look at some common design elements, and then we're going to talk a little bit about connections and details and important highlights and limitations of common details. For this presentation, we're going to cover a lot of different items that are particular to the Masonry Society Building Code requirements and specifications for masonry structures, commonly referred to as TMS 402 and 602. The 402 section of the code is really a designer-oriented section for how to design different elements, and the TMS 602 really is going to be a contractor inspector-oriented, really kind of covering the stuff about how to build things. And then at the end of the TMS code, there's going to be checklists that are going to be useful for analysis, design, and construction. It's always good to go over what some of the different companion documents are going to be, looking at the different masonry codes through the years. So the 2013, what was then referred to as the MSJC, that was a document that was put together by a group of people from TMS and from ACI and from ASCE, was referred to as the MSJC. So in 2013, that was referenced by the 2015 International Building Code. In 2016, it simply became TMS 402-602, which was then referenced by both the 18 IBC and the 21 IBC. And bringing us all the way to today, the current masonry code is the 2022 TMS 402-602 code, which is going to be referenced by the 2024 International Building Code. So looking at a definition of elements, looking at what is a masonry wall within the TMS code, we're going to see the wall is going to be defined as something that's 3 times longer than it is thick. So an 8-inch thick masonry element would need to be 24 inches long to use the wall provisions of the code. 12 inches thick would need to be 36 inches long. There's also going to be references to load-bearing elements, load-bearing walls within the code, and a load-bearing wall is going to be anything that has greater than 200 pounds per foot weight in addition to the self-weight that's loaded onto the wall. TMS 402-602 also looks at lintels or beams, masonry elements that span horizontally. They're going to have bottom bars within those elements. They're also going to have top bars. And a lot of the current analyses and designs, you're going to see that the lintel element is going to be connected to the wall elements that frame into it, that it frames into on each side. So oftentimes when you have that continuity, you have a fixed beam type condition, which would give us a negative moment in top bars generally being required. The code also covers detailing for stirrups. If you need stirrups, a lot of times you would simply increase the amount of depth of the lintel to alleviate the need for having any steel stirrups within the masonry beams, lintels. But certainly if you have a limited depth lintel, then stirrups would be fairly useful. Masonry columns are going to be elements that are going to be isolated elements for the structure. It's going to be an element that's going to be, say, at the edge of this canopy in the image on the right. So a minimum side dimension of 8 inches, reinforcement percentages of 0.25 to 4%, a minimum of 4 bars, lateral ties of a 1/4 inch diameter. So a lot of people like to use a smooth number 2 bar if it's available, but certainly number 3, number 4 bars could be used as well for ties. Lightly loaded columns would be columns that have a 2,000 pound or less unfactored axial load, not more than 12 feet high. And then when you have those situations with lightly loaded columns, you can simply use one number 4 bar and no ties in that situation. What are some of the masonry materials that we use to make up some of those wall, column, lintel elements? Oftentimes we have different types of concrete elements that we have to understand. First of all, we have the block, then we have mortar, then we have grout, and we also have several different kinds of reinforcement that we have to consider. We have vertical reinforcement, generally just for strength. We have horizontal reinforcement, which can be added for a wall for strength purposes, but also very often it's going to be really in the walls mainly for crack control purposes. And then, depending on the amount of horizontal reinforcement, we have to look at where control joints would need to be located for our designs. So, looking at wall reinforcement is going to be increasing the wall bending strength, certainly preventing cracks, as we just said. Within the strength design provisions of the code, we have a number 9 bar or smaller. And really, I think that's also just a practical limitation for using reinforcement within a masonry wall that has confined cells. Putting in something that would be larger than that would be one very heavy, two very long lap lengths, or and then considering different types of laps, just a larger bar would be very difficult to work with within a confined space of a masonry wall. There's other provisions for bar diameter to overall wall thickness and bar area to cell area that you have to consider within the code. For the notes that we're going to be putting on the drawings, we have several recommendations that we would like designers to consider. First, under material notes, we'll talk about what some of the different material definitions that we would like to see, or that we would recommend for designers to put on their drawings. Then look at the general notes that we put in there for masonry design. And then there's three really big recommendations that we strongly recommend designers don't do. And so, in fact, when we do project reviews, when I've looked at projects, I see some of these items. In fact, I just had one earlier today where I saw several of these items included in their old general notes. So don't define reinforcing in notes. Generally, what happens is designers like to use catch-all criteria to make sure that whatever they missed maybe will be caught by a general note, and that's just going to lead to a very conservative and probably costly masonry design. So we don't like to see reinforcing in the notes. We really want to see that defined with an actual schedule where we have a good use of material that's being considered. We also want to make sure that we don't define control joint locations in the notes. Oftentimes, we see designers try to use criteria, define criteria within the notes for control joints. And the problem with that is it really, depending on where the control joints are located, is going to really affect the overall capacity of the masonry walls. So, control joints really should be just referenced to see the plans or elevations for control joint locations, is really the only note that you should define within the general notes for masonry. And lastly, we don't want to see splice lengths defined just within a notes. It's often been defined by very simple terms for lap splices for reinforcing bars, and we have much better research and much better um, um, definitions for lap splices that we would like to see, and we'll talk about that in a bit. So looking at the material strengths, really with the material strengths, we want to make sure that we're referencing each component for the masonry items, the concrete items that are going to be used to build up, to build together, to compromise, to be put together to create the masonry wall. So first of all, we have the block that's going to be an ASTM C90 spec, and then we have a grout that's going to be ASTM C 476, and then we have mortar ASTM C70, and really all of those different elements are going to have their own attributes. When we put them together, it's going to be what we would then call a masonry wall. None of the items separately are going to be masonry, but when we put them together, it would be the masonry wall assembly. So the masonry assembly strength is going to be denoted as F prime M. And there's two different methods that we utilize to determine what the overall strength of masonry is going to be. The first one we would commonly refer to as the unit strength method. There's going to be several tables within the code that give us a very straightforward way to define what the masonry strength should be. And so when I talk about tables and I talk about very straightforward, usually what that means is there's going to be a conservatism that is built into the tables, and that's definitely the case here for the unit strength method. The more exact and precise way to determine the overall strength of the masonry assembly is to do prism test based on the actual materials that are going to be used. The reason why people choose the unit strength method is just due to timing. When designers are designing the masonry elements within a building, oftentimes they don't have the materials selected yet. Oftentimes the contractor and block suppliers have not been selected. So that's why the unit strength method can certainly be more convenient. But it always should be noted that the prism test method is definitely something that would give you more accurate results and oftentimes more economical solutions. So again, the F prime M for concrete masonry is going to be based on tables within the TMS code book. It's actually going to be within the specification section, the TMS 602. Within the TMS 602, there's a table that defines the overall assembly strengths. And so this table is going to be defining first in the left column, it's going to give you your F prime M. It's going to be the actual strength of assembly. And so really this table built for contractors that are going to be going out and finding the materials that they would need for determining this overall F prime M. The F prime M is then going to define what mortar you can use. So you either use type M or type S, and the block strength that will be associated with that mortar to get an overall F prime M. So it's really meant to be created for contractors so that contractors can really quickly understand what the actual strength that they need to meet and how to find the materials to meet that overall strength. So as a designer, if I was to think about this a little bit differently, I could rearrange these numbers pretty quickly and easily. Again, going from left to right, if I'm a designer and I want to do a little bit of research, I can understand what the actual unit strengths are going to be available in the area of my project. So determining what the F prime CMU value would be based on availability. We can then define the mortar type that we want to use, and type S is what I've selected here. And then given those two values, I can determine the overall strength of masonry. So again, the last two tables and the last two slides are the same tables, just kind of reoriented for whether a contractor perspective or an engineering perspective. Looking really quickly at the prism test method, again, the ASTM C1314 is going to give us the ways to determine strength based on prism test. So it's going to be the average of three prisms, but not more than the strength of the masonry units themselves. So again, what we're simply going to do is we're going to define these tests, and whatever the strength is, the average of the three is going to be the F prime M, the strength of the system. So it's a really straightforward test. We're simply going to build three different block and mortar assemblies, or block, mortar, and grout. The code is going to give us the latitude to use either two or all three of the materials that are going to make up the masonry wall. And then we're simply going to be testing them. We're going to be loading them one at a time, and then we're going to be testing them to see what the overall average strength would be for each one of the samples. And then once we determine the overall strength of those samples, simply adding them together, dividing by 3, is going to give us our strength of masonry for the system. Stepping back a little bit further, again, what are the different elements that are going to be making up this wall assembly? We have the block, the concrete masonry units that are going to be defined by ASTM C90. There's also clay elements and structural clay and veneers that would be different ASTMs that should be recognized. Really, the block is going to be the fundamental components of the wall. It's really going to be the key element to determine what the overall strength is of the wall. If I look at mortar, the second concrete element within the wall assembly, mortar is also going to be the other aesthetic item. So certainly block and block texture, mortar and mortar color are all going to be of significant interest to the architects and owners. But as engineers, what we really need to understand is with the blocks the materials are going to be, but then also what the mortar materials are going to be. Mortar is really going to be that cementitious material that we're going to use to bind together the units. So it's going to be something that's going to be, going to get hard after it sets. It's going to be made up of a mixture of sand, a binder element such as cement or lime, and then water. The mortar, when we test the mortar in isolation, the mortar is not going to be as strong as the overall mortar that would be used when it's placed within the assembly. And the reason for that is the mortar, when it's tested alone, it's going to have a higher water to cement ratio, and a higher water to cement ratio is going to yield a lower strength. The mortar, when it's tested alone, is also going to just be mortar cubes, which is going to be kind of a 1-to-1 ratio of size. When the mortar is placed within beds within the masonry units, it's really going to have a 3-to-1, approximately a 3-to-1 ratio of height to thickness. So those two factors really do actually change the strength of the mortar when we test it as an isolated element or when we test it within the wall assembly. So, again, the mortar is just meant to be the glue. There's different types of mortar. And so we just really have to look at and understand when we are going out to determine and specify mortar. What we want to do is we want to give the contractors the ability to either define mortar based on proportions. So then you have there's certain levels of different elements that you're going to use, or based on properties. So then you do that mortar only compressive test. We don't need to have contractors meeting both of these. Just one or the other can be used. So again, based on the code, we have the table, the assembly strength for the elements. From that, we know what block strength we need based on the mortar type that we select. And so all of those things are now coming together to determine our overall strength of assembly. There's just a little bit more that we want to take care to notice about mortar. Mortar, in addition to the three different types that we have, type M, type S, and type N, also there's different categories of mortar. Sometimes this is going to be more or less relevant to the engineer, but it is important to understand the differences in case a contractor wants to use a different type of mortar than maybe you were anticipating. So masonry cement is going to be probably the most common mortar that's going to be used. It's going to be pre-mixed with sand and water and ready to be applied on projects. If you have a historical preservation project, maybe you want to consider a Portland cement lime mortar. That's going to be what's found in older buildings and maybe could be a little bit better of a match. Or maybe you're in a higher seismic area. So in the more recent history, mortar cement was actually developed for having a higher tensile capacity. So mortar cement would be something that would be a little bit better to use in a higher seismic area for design. But like I said, the most common is going to be the masonry cement. Some typical questions that we tend to get is what type of mortar should we be specifying? So if we have all these different types and categories, what should we be specifying? And just a quick summary is type M is high strength in terms of the mortar cube tests, the mortar isolated test that we do, but it doesn't necessarily end in an overall assembly strength gain, especially when we look at like the unit strength method. You can see that kind of levels out to be very similar to what type S is. So type M can be used below grade, and it can be used in high load applications or extreme environmental conditions. But the fact of the matter is type S can also be used below grade. Type S can also be used in all seismic design categories A, B, C, D, E, and F. And really, type S can really be used in any structural application. So type S is going to be what contractors would strongly prefer to use. I've actually had masons tell me that they refuse to use type M. It's just really hard to work with, hard to clean. It's just not an easy mortar for them to work with. They would strongly prefer to use type S. We also have type N, which is also available, and it's going to be the weaker of the three. So it's going to be commonly used in non-structural or non-loaded applications such as veneer walls. Maybe we would even recommend type N mortar for veneer walls. It also could be used in partition walls where there's not much structural demand other than the actual holding up of the element itself. Type N mortar can't be used below grade and it can't be used in the higher seismic design category. So really, I think between Type S and Type N, you're going to be covering all the different needs that you would have. Um, and I would definitely recommend, based on application, using one of those two different mortars. It's important to recognize that we also have grout. Grout's going to be the fluid concrete that we're going to be pouring into the confined spaces that probably often have reinforcement within them. So something that's got a high slump is going to be very important to be used as grout. Fluid concrete, it could be fine, it could be coarse, or it could be a self consolidated grout, which is really going to be very fluid. But the very, very important aspect about grout is it's not the same as mortar. We still do get that question from time to time about what the actual grout can be, if it can be interchanged with the mortar, and that's definitely not. They're very different mixes and they have very different purposes to be used within masonry. It's also important to recognize that within the code, we're coming up with the overall assembly strength based on mortar type and unit strength. So once we have the unit strength and the mortar type, then we get the overall strength of masonry. Grout is then going to be a dependent kind of variable. We need to have grout that's going to be at least 2,000 psi or greater than F prime M. So having grout strength at least 2,000 or the strength of the overall assembly that was set by mortar type and unit strength. Just one other thing to mention about a grout is understanding what the different pour heights and lift height options there are. Within the code, within the TMS 602, it gives contractors a very good guide for how to place grout depending on the size of cell, depending on height that they want to pour a grout lift, or actually have the grout lift within the grout pour is what I should say. And the diagram on the right does give us a really good illustration for what would define a grout pour height and what would define the different lift heights. What I would try to do is make sure that as a designer, that I do give the contractor some ability to choose the lift heights that they would like to use, grout pour heights that they would like to use as they're building the masonry wall. The code is very clear definitions for the things that they would have to do to meet the different heights for both grout pour lifts. So again, back to what we recommend for notes for the project is not good enough to just indicate the F prime M value. What we really want to see is F prime M defined, but then we also want to see what the so if we, for example, if we have a masonry assembly strength of F prime M of 2,500 psi, then we also want to specify the block strength being F prime CMU of a certain value here, 3250 or greater. We know that we want to use type S mortar, and then we also then know that if our F prime M is 2,500, then our grout strength should at least be 2,500 psi. Again, before we made points about not specifying catch-all statements, not defining reinforcing, not defining maximum reinforcing spacing. Really, if you do that, then you eliminate the possibility to have unreinforced walls, which are a reasonable option in different areas of the country. And so we really want to have very specific tables to define the reinforcing for a project. We don't necessarily need to add top of wall bond beams to project. Again, that was going to be something that maybe was be necessary if it was a shear wall. But if we do have just, again, partition walls or non-load bearing walls that are not shear walls, there's certainly a lot of potential for lighter reinforcement options, maybe just joint reinforcement at the top of walls, and not putting in bond beams, because they're just going to be an expensive option. They're going to be hard to place the bars and hard to grout at the top of the wall. Again, we don't want to define control joint spacing via notes. For one, if you do have clay and concrete, one's going to expand, one's going to contract, one has reinforcement, one doesn't. So movement joints are going to be very different between maybe different masonry materials on a project. Really specifying the control joint locations is really going to have a lot to do with the overall capacity of masonry from a variety of different lenses. So it's very important that as designers, we put specific locations for movement joints on plans and elevations, and don't try to define it with words. The code is pretty strong on this topic. It definitely wants designers to locate them specifically, and it actually says it within mandatory checklists within the code. Going beyond the code a little bit, I think it's important to recognize that you do have different options when you have reinforcement within masonry walls. Sometimes you can have horizontal reinforcement, light amount of horizontal reinforcement, and regularly spaced control joints. I'm going to be referencing a document from CMHA, CMU Tech 9-25 is going to be a good document to understand the amount of horizontal reinforcement that you would need for a wall. And if you use a light amount of reinforcement, the 0.0007 area of steel to area of concrete masonry, you can see that placing regular control joints, um, maybe around 25'4" or 1.5 times the height of the wall. There's other limitations and reasons for adding control joints, maybe a differential supports, so on and so forth. But putting regularly spaced control joints when we have a light amount of reinforcement is the most common option that I see for masonry. But it also should be recognized that if you increase the amount of horizontal reinforcement, use a horizontal reinforcement ratio of 0.002, so that's about 3 times the amount of horizontal reinforcement, either as rebar in bond beams at 48 inches on center or less, then you can minimize or maybe eliminate control joints in certain parts of your masonry design. The third option would be, again, using that same amount of horizontal reinforcement as a combination of joint reinforcement and rebar. And we'll talk about maybe why that comes into play in a few slides. But anyway, we want to look at maybe where this would be applicable. This is just kind of a classic example of something that has multiple different dock doors. We have limited space on the piers, so this is a plan view. You can see limited locations to where we could actually put in a control joint. We'd be really kind of splitting that pier and maybe really diminishing the capacity of that pier. So again, if we look at it in elevation, you can see if I would have to put a control joint someplace within these piers, that would really diminish the overall capacity of that design. So recognizing potential reinforcement that we would have within this elevation, say we have masonry lintels over these doors. We're a strong advocate for masonry lintels within masonry walls. So you have horizontal reinforcement in those lintels that we can make continuous. We have a roof support bond beam that's going to be a continuous reinforcement. And then we're also going to have a top of wall reinforcement that can be continuous. So, with all of that reinforcement and the potential for joint reinforcement, we have more than enough opportunities to have enough horizontal reinforcement so that we don't need control joints in that part of the elevation. So you can see what I have highlighted here in green is going to be areas maybe where we cannot put control joints in the masonry elevation. But then maybe the rest of the building has standard block walls. We have rectangular walls that we can go back to lightly reinforcing, light horizontal reinforcement, and control joint spacing around 25'4", plus or minus, depending on height of the wall and support conditions. So again, it's pretty easy to see that that area around those doors can have plenty of reinforcement to prevent any cracks from occurring. But then you can go back to the standard practice for the rest of the building um, with control joints and horizontal joint reinforcement. And again, just to emphasize the point, looking at the cross section, you can see all of the opportunities for horizontal reinforcement. First of all, you have the continuous bond beams and lintels just over the doors. Then we have again the roof joist bearing elevation where we're going to have another bond beam and continuous reinforcement. And then at the top of the wall, we're going to have again an opportunity to have continuous reinforcement. So all of that reinforcement together really kind of comes together to have plenty of horizontal reinforcement for limiting the number of control joints in that elevation. Next, we're going to take a quick look at lap splices. Lap splices that we said before, we don't want to have those defined in the notes. We also have good testing that shows all these different variables, bar sizes, reinforcement location, whether in the center or at each face, spacing and wall strength. All of those variables are going to affect the overall lap splice lengths that we're going to need within designs. So just a couple details. I mean, certainly putting details together to show where the lapse places are, what those links would be. Maybe having a table defining the overall lapse place length would be very good for giving different bar sizes. You're going to notice that we actually have two different rows here for, say, different bar sizes. If we have two bars used within a cell, then we actually need a longer lap splice just because the cover is going to be reduced, the spacing is going to be reduced. So there's a couple different examples here, or another example here from the Block Design Collective, where you can see some standard tables being developed for different thickness of walls and different bar sizes in the design. Next, we're going to move to some what I would call prototypes. If we do have partition walls are going to be non-structurally loaded elements within a design. We know that we're going to have a standard loading condition for those elements. And so really that can become a prototype for our design. We really can define tables for that design. The code is coming out and being very explicit about partition walls, that they don't have any other structural function other than defining spaces. So they just need to hold themselves up. It's very different than shear walls. Shear walls have a lot of reinforcement requirements. They have definitions for the different types of masonry shear walls. We can have an ordinary masonry shear wall. We can have ordinary reinforced and intermediate reinforced, but then also specially reinforced masonry shear walls. When you have masonry shear walls, you have certain reinforcement requirements. Two that I have highlighted here is two that I see getting carried over into partition wall design. The reinforcement at the top of the wall and the vertical reinforcement in an intermediate reinforced masonry shear wall, no further apart than 48 inches on center. Really, within partition walls, we don't have to have that top of wall reinforcement, and we don't have any limitations on the spacing of reinforcement, like a 48 inches on center. So I would say partition walls are getting too complicated. They're getting too much reinforcement, and we really do need to simplify them. And the reason that I say that we need to simplify them is really when we look at this, and designers are looking at value engineering projects. Oftentimes, when people look at a partition wall that's over designed, or maybe should say under designed and over use of materials within the partition wall is maybe the more appropriate thing to say. We have too much unnecessary horizontal reinforcement. We have not needed within the lower seismic design categories. We have the possibility for not needing the top of wall bond beam. So we certainly want to eliminate that if we can. We want to minimize the vertical reinforcement. So if we can pull out some of that reinforcement, certainly that'll then also limit the locations and size of the top of wall connections. That really only needs to happen at those vertical reinforcement locations. So we have a lot of opportunities to have a much more economical partition walls that can be used. Again, within the Block Design Collective, there are some standard details for connecting that top of wall. Here you can see detail showing a bond beam near the top, or the detail on the bottom left showing horizontal joint reinforcement used at the top of the wall and no bond beam. But either way, we have a lot less reinforcement that we would be able to use because it is a partition wall. In fact, we also created some tables for reference, tables for all the different reinforcement that you would need for a standard partition wall with 5 PSF of service load in a seismic design category A or B. Really, most of the wall can be, or most of the different design options, I should say, can be unreinforced. So you can see a 6-inch wall going up to 12 feet can be unreinforced. 8-inch partition wall could go all the way up to 16 feet and still be unreinforced. 10-inch up to 20 and 12-inch up to 24. So really, you can see that we can have some significant heights that we can achieve with those partition walls. We can also look at seismic design category C. So just a slight more demand on the wall because we have some reinforcement requirements that we have to use within seismic design category C. You can see a number 4 bar at 120 inches on center would be the maximum spacing that you would have for reinforcement. So you can see that it's not 48 inches on center, but 120 inches. So one number 4 bar and half-inch bar every 10 feet is the amount of reinforcement that you would need in a partition wall in seismic design category C. It's not until you get to seismic design category D, where you need bars at 48 inches on center, and seismic design categories E and F even have more requirements. But I think pointing out some of the standard tables that you can use for the lower seismic design categories can create prototypes for your overall design. In a very similar fashion, we have exterior non-load bearing walls that we can really treat in a very similar way. We have masonry walls, we have load bearing walls, we have these infill walls, which can be participating or non participating elements within design. So if it's an exterior non-load bearing wall, if it's a standard masonry wall, then we have wall between floors away from the structural frame, following certain code sections. If it's an infill wall, it's going to be constructed within the frame, bounded by the actual structural frame. Again, referencing TMS 402. The standard wall would have ASD or LRFD. Infill walls are just going to be LRFD options. We have different fee factors between a standard wall and infill walls. For flexure and axial shear, we have to accommodate the deflection for the floor above for a standard wall. And infill masonry walls within the code again are non-participating infill or participating infill, and really there's shear transfer with the participating infill, strut analysis with the participating infill. So all differences that you have to certainly make sure that we understand. Hopefully within the code we can bring some of these sections together to provide a little bit more clarity between the two. But nonetheless, we certainly can come up with an exterior non-load bearing wall table, very similar to the partition wall tables, which we could utilize certainly as a prototype for all designs across the country. Next, we want to look at the different details and connections that you could use within design. Just kind of a really quick overview for some standard details that we can use for all designs. First of all, we're going to look at the different connections to masonry walls. Do you have an embed plate or do you have a bearing plate? An embed plate might be better for tension connections, adequate for light, say, shear loads, but a bearing plate is going to have a lot more capacities for vertical loads. Let's kind of walk through what some of those examples look like. So again, an embed plate, where you'd actually face mount a plate on a masonry wall. It's relatively simple. You certainly can add these steel members, to connect to a masonry wall after the fact. You certainly probably have to look at whether it's grouted or non-grouted masonry wall to understand the full capacity for the anchors, but it's a good retrofit solution for adding a beam to an existing building. We also have the ability to have a masonry corbel. We have corbel connections that we still reference. I still give standard details out for what a corbel would look like within a masonry wall, either for just a masonry beam element or for, say, a continuous precast plank being supported on a wall. But nonetheless, corbels are still not that common today. It does require a change in thickness to create a seat for the elements that we're supporting. Probably the most common elements is going to be a beam pocket. It's going to be a very simple solution. It's going to be just simply leaving out face shells of the masonry and allowing the member being supported to be framing into the masonry wall. So it's going to be a little bit more complicated, a little bit more coordination with the actual floor elevations and the framing contractors. You do have to also pay a little bit of attention to fire ratings. If you're removing some face shells, you maybe have to replace that with some grout and mortar filled elements around the member that's framing into the masonry wall. So again, there's a variety of different ways that you can have bearing plates. It could be just a pocket. It could be into the end of the wall that you can see in this design scenario. So again, looking at the bearing plate capacity is another thing that we can have a standard connection that we can define for a masonry wall. Looking at the different types of capacities that you can reference, having a bearing plate on a wall really comes down to a bearing area, whether that it's going to be a confined bearing area or something that's unconfined. So if the bearing plate is going to be near the face of the masonry wall, it's going to be what I would call an unconfined condition, versus if the bearing plate is slid interior to the wall, then you'd have a confined bearing capacity, which is more capacity for your design. So here you can see a sample of some calculations for looking at a bearing plate analysis, looking at the bearing area depending on where the plate is. As the plate gets closer to the face, you actually have, again, the unconfined bearing area, and that was actually going to give you less and less capacity. So it's just kind of a quick overall summary. An embed plate or bearing plate. The embed plate might be better for an exterior connected to the face of the masonry wall. Maybe that's going to be something that's going to be good for connecting to an existing masonry wall. But the bearing plate's going to have a lot more vertical shear load capacity. So it might be more likely that you could use that for typical framing into a masonry wall. Again, a standard detail here from the Block Design Collective for what some of the bearing plate schedules could look like and what the detail could look like in design. Next, we're going to look at masonry or steel lintels. How do you look at the elements that span the openings uh, that you have within a masonry wall? Masonry lintels are going to be elements that are going to be very integral with the rest of the wall around them. It's going to be a very robust design. It's going to be an element of the wall. So there's going to be a lot of continuity between a masonry lintel, and the walls on each side. Steel lintels, I would say, are foreign, isolated elements. It's a different material. It's got different material properties, different architectural considerations, and so really looking at the different types of materials that we want to use for lintels can have large impacts on the overall cost for a design. So here we can look at just kind of a standard elevation. You can see that a designer was evaluating whether or not they wanted to use steel beams for their design. You can look at the steel beams and how it's going to frame into those piers and the pockets that would create and the joints that it would create. So really the steel is going to be quite difficult to work with versus a continuous masonry lintel. And again, if you think back to the control joint conversation that we have, if we have masonry lintels, we can have continuity across that elevation, and we could certainly have a very robust lintel design and analysis. So again, steel lintels are going to be fairly complicated and very costly. They have been very common. They were certainly more common and more typical when we had unreinforced masonry. So now they're critical. They have the need to protect them. Certainly, you're going to have to paint them. You're going to have them galvanized, something to prevent them from rusting. Bearing plates are often required. They're not resistant to fire. There's a large thermal bridging issue. Certainly, anytime that you have steel elements, we have to consider how the thermal transfer is going to happen for the design. But the other part of the thermal loading that you would have when you have a steel lintel is the steel is going to change size more rapidly than masonry walls. So what you have is you have a change in temperature is really going to create a stress for those steel beam bearing locations because the thermal load is going to change the steel size more quickly than the masonry around it, so the steel is either going to shrink or expand faster than the masonry wall, and it's pretty unforgiving if it's connected, if it's hard connected to the masonry elements. It does cause massive amounts of loads if it's not allowed to slip or slide at those bearing locations. So the thermal bridging does become more than just a transfer thermal bridging, but the thermal loads becomes an even larger issue, which is why we see a lot of potential problems using steel lintels. But the real reason why we're moving away from steel lintels is it was really just used to solve shoring. Again, when we had an unreinforced masonry design, typically maybe that was prudent. But now that we have reinforced masonry elements, reinforced masonry lintels, there really isn't a need to solve the shoring. We have some very elegant shoring solutions today. We also have prefabricating masonry lintels that we use today that eliminates the need for steel being used to resolve shoring. So again, it's complicated to do right, and it certainly can cause a lot of problems. Masonry lintels are going to be as fast. It's going to be it's something that can be built with the rest of the wall. It's going to be economical. It's going to be far less cost than a steel lintel, and really that's independent of the size of the opening. The steel lintels are always going to cost more. Masonry certainly has the better aesthetic. It's going to look the same as the rest of the wall around it. The thermal loading issue is going to be far less to almost eliminated. Um, You can have it built in place. You could have it prefabricated. You have a lot of abilities to solve shoring. They can easily go 10 feet. You can go 12 feet very typically, but we can go even further with better analysis methods. So again, masonry lintels are going to be more integral with the masonry wall. They really do create a robust, efficient design. And again, we have a very nice detail here from the Block Design Collective. Next, we're just going to do a quick comparison here for masonry or steel columns. The reason why we bring this up is a masonry pier or masonry columns do have a lot of capacity. And I think that's always important to remind ourselves as we're evaluating different elements, as we're detailing different elements. So if you can resolve the forces with masonry elements that are going to be within a masonry wall, certainly that's going to be a better construction method and better material usage. Um, so just doing some really quick comparisons, we look at a masonry column, a 16 by 16 column with a certain strength, and we can see the actual forces. So again, these are all for a certain similar length for whether it's a masonry concrete column, a masonry pilaster, where you have actually the kind of column element plus some flanges that would be considered. You can see more and more capacity. So a masonry column is going to have a little bit less than a concrete column, but a masonry pilaster of a similar size with the flanges is going to have more capacity than the concrete column. So you can see that before 16 by 16 and also 24 by 24. And then all of those values as they relate to, say, a similar HSS 12 by 12 element um, that would have to be then confined within the masonry. You'd have to cut the masonry to enclose this steel element. So there's a lot of complications for that type of design. So that's when you have a bump out. If you didn't have a bump out, if you wanted to have a flush masonry pilaster, again, you can see some of the different capacity comparisons between 24 by 8 inch masonry pilaster, 24 by 4 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 by 4, and then an HSS 5 by 5, which would be the column size that you would need to fit within an 8-inch masonry wall. So again, just some numbers to compare the different elements. Next, we're going to jump quickly to roof details, some of the different comments that we would make on roof details. Looking at joist bearing conditions, it's very common for the SGI manual to point out that we need a 4-inch bearing from a joist to a bearing plate, but that's just not what you need. It's what they recommend. You can get much shorter bearing condition from a joist down to 2.5 inches. So it's just something that you always want to ask for so that we can reduce the size of the bearing plate to just what we need. And then that bearing plate, if we can put that somewhere in the center of the course, that certainly eliminates any of the eccentricity that you would have from that design, but it also is going to give us a confined bearing capacity, which we talked about earlier, being a large benefit. Also, we want to be very careful when we connect steel to masonry and what the masonry does the masonry have the ability to flex or move, because steel, again, as the thermal loads from steel framing into masonry, steel is going to change size quickly, and making sure that we have some allowance for that in construction. So again, very similar comments for joist girders. We're going to have a larger reaction, probably a larger bearing plate. We again have to think about if we're framing into the wall, do we have fire protection? Do we have to somehow use mortar and grout to enclose this element? Do we have the ability to slide the bearing plate to the center of the wall? Do we want to make sure that we have a good stud length from the bottom of the bearing plate? We don't want to have too long of a stud length that would conflict with other masonry elements in design. So there's a few different things that we would look at there. And again, considering how we're connecting to the masonry wall, does the wall have the ability to accommodate the shortening or lengthening of that steel due to thermal loads during construction? And all the same comments for a steel beam. Steel beams probably even higher reactions, higher bearing, bigger bearing plates. But again, fire protection. Remembering, if the steel is framing into the wall, what are the thermal loads? Does it have the ability to move? What does that look like for our overall design? Really, and when it comes to a steel beam, because we have so much force that could be accumulating if we have a thermal, again, a 60 or 80 degree change in temperature would not be completely uncommon over a couple days. on a construction site. So just recognizing what the force would be. Does your masonry have the ability to flex, or do we have to make sure that we have some sort of a slotted connection so that the steel can move without imparting too much force on the concrete masonry wall? We have details from the Block Design and Collective, a lot of standard details that use in reference for these designs as well. Last, we're going to move into foundation wall designs. Foundation wall designs are usually, especially for a stem wall, not going to be overly critical because the structural demand on them is not too high. Really, the walls become relatively thick relative to the elements that are sitting on the wall. So it comes down to a compatibility issue. Recognizing that the stem wall is going to be there, it's going to have multiple layers of design above, whether it's a masonry wall, cavity wall, um, whatever different types of elements. So again, the only thing that I would like to point out here is you don't need to grout it solid below grade, or certainly you don't have to grout the whole stem wall. Maybe just the top course could have a bond beam and grout within that top course, but most of the masonry below grade can be left ungrouted for a design, which saves an incredible amount of material and cost. So we have another detail that we want to reference here, or then there's a whole group of details from the Block Design Collective that you can look at for below grade as well. So, in conclusion, for the connections for masonry walls, we have masonry notes for structural drawings, some what to avoid, and some things that we recommend included. We have some standard 2D details, 3D details that we can recommend utilizing. So, certainly understand the limits of each detail. All the details from the Block Design Collective have designer notes to them, which certainly can be a good aid in where to use the details. So we have a lot of different references, a lot of different sources that we utilized and referenced today, but really just different elements that are along the way to create your overall final design. So with that, we want to thank you for your time. Hopefully, you can download any of the information that we have referenced here within this presentation. If you do have any questions, you can certainly reach out to me, Sam at Force, Forse, consulting.com. Thank you.